Well, thank you very much, Fred, for that kind introduction. And just a little bit more about my background. I'm going to be talking about the Cassini mission at Saturn, circling Saturn for 13 years, returning data. And when I first started working on Cassini 30 years ago, my youngest daughter had just started kindergarten. And now she's married with a daughter of her own. So you can see that these missions can literally span a lifetime. And actually, my granddaughter was actually with us for the end of the Cassini mission. And in so many ways, Cassini's findings have revolutionized our understanding of the Saturn system, really changed the way we look at the solar system and our own planet as well. And so I'm going to share some of that with you, some of the wonders of Saturn and some of Cassini's intriguing discoveries. Well, I have very fond memories of coming to Canberra. We were here in 2016 in November, so it's almost exactly 3 years ago. And we went out to Tidbinbilla, to the Deep Space Network station there, because we knew that big 70-meter dish would get the very last, data coming back from Cassini. So the very last whisper of information would come down to Canberra. And so we visited the people there, and there's a picture of my husband Tom and I, and we saw they had a Cassini drive out there in Tidbinbilla, and that was very exciting as well. Well, why do we explore space? Why do we not just look from the Earth with our telescopes? Why send spacecraft into space? Well, I'm going to tell you about two of the grand questions that we go out to answer. And the first is, are we alone in the universe? Has life originated somewhere other than the Earth? And how did life originate on our own planet as well? And Cassini has provided us some clues in answer to that question. Another grand question is, how did the solar system and the Earth within it come to be? How is it evolving? Where are we headed with the solar system? What you can see displayed here are the 8 planets in our solar system, the inner 4 small planets, Mercury, Venus, Earth, and our moon, Mars, the asteroid belt, and then the gas giant planets, Jupiter, the biggest planet in our solar system, Saturn, the second largest, and then Uranus and Neptune. We've actually had a chance to visit all of these planets. And in fact, the last 2, Uranus and Neptune, have only been visited by the Voyager spacecraft. And that's the first project I worked on when I started at JPL way back in 1977. And I think it'd be great to go back to that place. I think it'd be very interesting to see it. Well, how about Saturn? Saturn is a big ball of gas made mostly of hydrogen and helium. And it's, I say giant planet. Well, how big is that? Here is our Earth and the moon and the distance between them to scale. And if we put Saturn in that picture, Saturn plus the rings, it's huge. 764 Earths it would take to fill up the volume of Saturn. So you can see Saturn plus the rings fit in between the Earth and the moon, but being made mostly of hydrogen and helium, very light gases. If you could build a bathtub big enough for it, Saturn would float. Can you imagine that? A big bathtub with Saturn floating in it. So we've looked at Saturn with other missions, and here's just a summary of those over the last 40 years. First of all, we had the Pioneer 11 flyby in 1979, and that picture off to your right is a picture taken by Pioneer. Next, we had Voyager 1 and 2 flyby in the early 1980s, and there's a Voyager family portrait of Saturn and the moons as seen from Voyager. And one of those moons, Titan, what remained a mystery after the Voyager flybys. Titan had this thick haze surrounding it, like a really smoky day around here, and you couldn't see through to the surface. And so we wanted to go back, in particular, go back with something to land on the surface and study Titan in more detail. And you can see some pictures from Cassini on the bottom there. Well, here's next a picture of the Cassini spacecraft and of the Huygens probe. Cassini spacecraft is about 6.5 meters tall. That big white antenna is about 4 meters across. And you can see people in that image to give you an idea of the scale of the Cassini spacecraft. That big gold object on the front is the Huygens probe, and that's provided by the European Space Agency. So they built it, provided it to us, and so Huygens was a passenger on Cassini all the way to Saturn. Now, the Cassini spacecraft is named after a famous astronomer, Jean-Dominique Cassini, who discovered a gap in Saturn's rings, named the Cassini division in his honor. So it seemed appropriate to name a mission back to Saturn in his honor. And the Huygens probe is named after a Dutch astronomer, Christian Huygens, who discovered Titan. And so for a probe to parachute through to the surface of that moon, it seemed appropriate to pick the name Huygens. Now you'll notice that Cassini is covered with gold-colored blankets. Usually when you see spacecraft, they often have black blankets. But Cassini actually had to make a circuitous route in the inner solar system, 2 flybys of Venus, 1 of the Earth, Jupiter, and on out to Saturn, using the gravity of these objects to slingshot Cassini's way out to Saturn. So going in close to Venus, we had to cover it with gold blankets to reflect the heat from the sun in at the distance of Venus. Now, as my daughters were growing up, this is my daughter Jessica, we would go periodically to see the Cassini spacecraft being built. And so we're dressed to be in the clean room, and we're looking over Cassini right before they took the spacecraft down to the Cape. Now, Cassini is an international mission. Here are the flags of some of the 19 countries that participated, providing hardware, scientists, engineers. The European Space Agency provided the probe, and the Italian Space Agency provided the high-gain antenna on board Cassini. Here's another view of the Cassini spacecraft in more detail. 3 packages of instruments. The optical remote sensing instruments include the cameras, both a narrow and wide-angle camera, and we could look across the spectrum from the short ultraviolet into the far infrared to look with all different kinds of colors and wavelengths of what we could see in the system and learn about it. The high-gain antenna is actually an instrument too. The radio signal can go through the atmosphere or through the rings, and we use the antenna for radar to map the surface of Saturn's moon Titan. And then a whole host of 6 fields and particles instruments to measure the magnetic fields, protons, electrons in the environment around the spacecraft. Now I want to share with you Cassini's launch. Cassini launched in October 1997, and we took our daughters out of school for a week so they could be there with us to witness Cassini's launch.
T-minus 15 seconds. T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in, roll program is in. We have cleared the tower, and the Cassini spacecraft is on its way to Saturn. T plus 20 seconds. All systems are go. Jupiter Inlet Tracking Station now acquiring data. All systems go.
It was a spectacular launch before dawn. We looked in the distance and could see Cassini slowly lifting off the launch pad, but it was silent. And then the waves of sound from the roar of the rocket engines, you could just feel it against your skin for that launch. And it was a pre-dawn launch, and with the teenagers, we told them, well, you're going to have to get up awfully early to go see this launch, but it'll be worth it. And so they joined us. So you notice it went up through into a cloud, and the cloud brightened. At first, I remember holding my breath thinking, did the rocket explode? You know, what's going on? And then very slowly, Cassini lifted up through that cloud. Well, here's a view of the Cassini mission against the 30-year orbital period of Saturn. So I can proudly say I've worked on Cassini for 1 Saturn year. We picked the instruments in 1990, spent 7 years building them, launched from the Earth, as I said, 2 flybys of Venus, 1 of the Earth, Jupiter, on out to Saturn, arriving in 2004. We arrived just a couple of years after northern winter solstice. We had a 4-year prime mission planned. Everything went so well, NASA said, okay, we're going to give you money for another part of your mission. 2-year equinox mission with the rings edge onto the sun. Really an interesting time for a ring scientist like me to really probe the 3-dimensional structure of the rings. And then a 7-year solstice mission lasting until 2017, northern summer solstice. And in this green box is a set of proximal, or what we call grand finale orbits, where we took Cassini and actually dove in between the rings and the top of Saturn's atmosphere before sending Cassini into Saturn's atmosphere itself. Here's another way to look at the mission. You can see all of the orbits. We circled Saturn 294 times. We had 127 flybys of the moon Titan. We used Titan's gravity to shape our orbit, its inclination and orientation. 3 close flybys of a very tiny moon, Enceladus. Enceladus was so amazing, we added 20 more flybys of that moon in the rest of the mission. Additional flybys of the other icy moons. These are our final 22 grand finale orbits. And here you can see the seasons change from the northern hemisphere perspective on Saturn. Now, if you were to look at all those 294 orbits, here's what you would see. Buried there in the middle is Saturn. You can't even see it. These gray orbits are where we started the mission. You can see the way we changed, look to the poles of Saturn, and these green orbits here are the final orbits of the last 6 months of the Cassini mission. And so you can see if you have a big moon like Titan, you can do a lot. It's like having an extra fuel tank on board to help you shape the mission. And here are just some interesting facts. I won't go through all of those, but we sent 2.5 million commands to the spacecraft, 635 gigabits of data over the 13 years of the mission. And yet when you look at something like the CERN Super Collider in Switzerland, they get twice that much data in a fraction of a second. But for Cassini, that represented almost 500,000 pictures and a lot of other data that we sent back. We've published now over 4,000 papers and traveled 4.9 billion miles by the end of the mission, or 7.9 billion kilometers. Well, let's start out and look a little bit at Saturn. And here is very interesting. We arrived at Saturn with the ring shadow covering up the northern hemisphere. And the atmosphere in the north that you can't see from the Earth looked bluish and almost reminded us of Neptune. Then at equinox, you can see the ring shadow is just this thin line around the equator of Saturn with the sun edge onto the rings. And finally, here toward the end of the mission, the ring shadow is in the south, and the bluish color is coming forward in the south. In a sense, the ring shadow is like a giant sundial on Saturn. If you look at a picture of Saturn and you can see where the ring shadow is, you know what season it is on Saturn. Here's a good example. This is the North Pole. You can see that bluish haze, especially prominent inside this feature we call the hexagon. And then as the sunlight falls in, those golden haze particles start to grow again. And you can see that golden color is coming back, and it's now getting bluish in the southern hemisphere. Here's a close-up view of the hexagon. It's a 6-sided jet stream, 2 Earths across. And it's the only hexagonal jet stream that we know of in the solar system. Just at the North Pole of Saturn, there's not a hexagon in the south. None of the other giant planets have one. And it was first discovered in the early 1980s by Voyager, and it's still there. And if you look carefully in this false color movie, the little clouds race around like horses on a racetrack on the edge of the hexagon, going at a very high speed. And if you look at the very center of the hexagon, you'll notice that there's a huge hurricane or typhoon. And here's a close-up false color view. This hurricane is about half the size of Australia, with winds blowing at hurricane speed right at the North Pole. There's another one right at the South Pole of Saturn, so in a very stable place. The sun's coming in from the right. You can actually see the shadow of the eye wall in this particular giant hurricane on Saturn. Now here's another view at different wavelengths. If you look in near infrared, you can see this is very deep in the atmosphere. Green is a little bit higher up, and blue are the highest clouds. Here's the difference in temperature. It's very warm, that the atmosphere is going down into this hurricane. And as it goes down, it's heated up to a higher temperature. So we can learn a lot about something like inside this giant hurricane by looking at different wavelengths. Now in 2010, we saw the development of a giant storm on Saturn. About once every 30 years, these storms start to develop and cover one complete latitude all the way around the planet. This one came 10 years early. I guess Saturn knew Cassini was there, we'd have a chance to watch this storm. So here's the head of the storm, and you can see its tail going around in the back. If you look in the near infrared, it's easier to see the head of the storm and the turbulence from the clouds, and you're looking higher up in the atmosphere. And if you look all the way out into the far infrared, it turns out that to generate a storm like this, Saturn is releasing a tremendous amount of energy. And so here, like a giant cyclops eye, is the heat coming out of Saturn from that particular storm. And that storm lasted over about 9 months before it slowly dissipated as it completely wrapped itself around Saturn. Another storm picture, we actually saw evidence of lightning. This little blue dot is lightning. The next picture, it's gone. Huge flashes of lightning, some of this equivalent to some of the very strongest lightning bolts that you'd see on the Earth, coming from very deep in the atmosphere from the water clouds there. Now let's move on to the rings. The rings have very simple names. They're just A, B, C, D, and then on out to the bright E ring, F ring, and G ring. And they're just named in the order that they're discovered. So that system had gotten started long ago. We decided, what the heck, we'll just stick with it. And so yeah, this very narrow ring is one of the rings that Pioneer first saw. Here's a color view of the rings. Here's the Cassini division, after which the astronomer, after which the mission is named. A couple of gaps, the Encke gap. There's another little gap called the Keeler gap. These two gaps actually have little moons inside of them. The B ring is very bright and has the most material. The rings on average are only about 10 meters thick and yet span hundreds of thousands of kilometers. They're made of particles millimeter size to centimeter size, mostly pure water ice, about 99% water ice. And some of the golden or the other colors come from pollution, from micrometeorites hitting the rings. The C and the D ring are thinner, and so they have more polluted material, and they're grayer or darker. Now here's the picture I showed you earlier. This is with Saturn equinox, where the sun is edge on to the rings, and the rings are only illuminated by light coming from Saturn itself. And to create this picture so that you could see the rings, we had to brighten up the rings by a factor of 20 on the left and by over a factor of 60 on the right, so that you could just get a hint of the rings being there. And what's unique is with the 10-meter thick rings and the sun edge on, anything bigger than 10 meters that sticks up above or below the rings will cast shadows. So in our images we took of the rings, we were looking for places that we could see shadows and we could find bigger objects. And this is one of my favorite pictures. This is the outer edge of the B ring. If I go back, here's the B ring and the Cassini division. So just on this outer edge, we looked and look at all these shadows. We knew that inside here there were objects maybe half a kilometer or so in size, casting these very long shadows. And a good analogy for these shadows is, imagine you're in the space station and you want to find the pyramids. If you're looking down at the Earth around noon, the pyramid shadows will be very small, and it'll be very hard to pick them out against the background of the sand. Now imagine you look at sunset, and then the shadows are very long, and all of a sudden you can start to easily pick out the pyramids. In the same way with very long shadows, we can pick out the biggest particles in the rings. It's like they get to the edge and they maybe accumulate like big snowballs and grow larger and larger until they can then cast these very, very interesting shadows. This was a very interesting finding about Saturn's rings. On the edge of the A ring, there was this little tiny cloud of dust. Here's a blow-up of that picture. And we knew that that dust was being kicked up from the formation of a tiny moon. So the ring particles were coming together into a larger and larger object and forming a tiny moon. And the scientist who discovered it in 2013, he first saw this cloud of dust and knew it was a moon on his mother-in-law's birthday. So he nicknamed, informally called this moon Peggy. And she thought, what a great birthday present to have this little moon named after me. And so for the next 4 years, we continued to see if Peggy might break free of the rings and become a little moon in her own, of her own. And even on the last day of the mission, we took pictures to see if Peggy had broken free. But alas, even at the end of the mission, Peggy was just still there at the edge of the A ring. So maybe a future mission will go back, and we'll find out what happened to Peggy. We think that maybe Saturn's moons formed from these tiny objects coming together and being spun out from the rings and then coming together to form Saturn's moons. So that's one idea, perhaps, of how you could get moons coming from the rings. Here's a picture from the Australian Astronomical Observatory that I really love. It's a spiral galaxy. It's called the Cartwheel Galaxy. What I like about it is you can so distinctly see the spiral arms coming out from it. And this spiral galaxy has something in common with Saturn's rings. Imagine taking this galaxy and wrapping it up very, very tightly so that the arms start to, go around and round in circles like that. That's exactly what places in Saturn's rings look like. And the same physics that applies in spiral galaxies we can use in Saturn's rings for these things called spiral density waves. Here's a picture of one of those. The wave is launched from here. It's a 2-to-1 resonance. What a resonance is if you have a ring particle at a certain place in the rings, in this case for Janus. Janus goes around Saturn exactly once. The ring particle goes around exactly twice, and it gets a kick at the same place in its orbit from Janus. Imagine pushing someone on a swing. And if you wait until they're at the top of their motion and push them again, you can make them go higher and higher. And in the same way, Janus is launching this wave, and so every other wavelength is a different spiral arm of this 2-armed spiral. Now, Janus shares an orbit with another moon, Prometheus, so every 4 years, there's a glitch in between the spacing of the waves. And so in a sense, you have a timeline here. You have, these are the youngest waves, and these are the older waves spun out by Janus. In fact, if you look in the leftmost corner, those waves were first launched in the early 1980s when Voyager was flying by Saturn. I think this is probably my very favorite picture. This is a backlit view of Saturn. It's a solar eclipse picture. Saturn is covering up the sun, so we can bring our cameras in very close to look at Saturn and look at the rings. And this only happened a couple of times during the entire mission where Cassini was lined up in a way that Saturn could cover up the sun. And if you look at this bright white ring around Saturn, that's where the sunlight gets refracted, bent through the atmosphere and sent to Cassini's cameras. And you're looking at every sunrise and every sunset on Saturn at the same time. And I really like this picture because you can see all of the rings. Here's the E ring. You can see the F ring on the edge here. Here's the G ring. All the tiny particles are sending light forward into Cassini's cameras. A good analogy, if you've ever had a really dusty windshield and you start to drive into the afternoon sun, all of a sudden it gets very hard to see. Those tiny particles send light forward, called forward scattering, into your eyes. Now this picture is important in another way because there's 3 other planets in this picture. Cassini actually got pictures of Mars, Venus, and the Earth and the Moon. And we spent 20 minutes taking a series of filters so that we could create a color image so you can clearly see this is the Earth and here's the Moon. And in fact, we knew well ahead of time we were going to do this. And so we said, let's tell everybody on Earth that can see Saturn at the time to go out and wave at Cassini during this picture. And so we did. So from the west coast of the United States, it was daylight all the way over into Europe, that part of the United States, and all into Europe. We said, go out and wave at Saturn. And so we told people where to look in the sky. And they did. They went out and waved at Saturn so that their photons could go out and be part of this picture of the Earth from 1 billion miles away. But of course, the Earth is only a few pixels across, so you're not going to be able to see any people in the picture. So we said, take selfies. Take a picture of yourself waving at Saturn and send those all the way over to us at JPL so we can see how many people are out waving at Saturn. We got pictures of families, astronomy clubs, people holding up their dog paws, their babies, all waving at Saturn. And so we took all of those selfies. We said, well, what are we going to do? We got thousands of selfies from around the world. And so we went out. In fact, who went out and waved at Saturn in 2013? Anybody here? Oh, good, yeah. Tom and I went out and waved at Saturn. We took all those selfies. We recreated that mosaic out of selfies. It was very popular because people wanted to know, where am I? in this great picture that we put together of Saturn. And so it's very popular. I have to admit, I went to find Tom and I in this picture too. So a little bit about Saturn's moons next. There are over 60 moons now discovered orbiting Saturn. A lot of them are well away from the planet, probably captured objects. You can see they come in all kinds of sizes and shapes, from tiny fragments all the way up to giant Titan. And for comparison, Titan is about the size of the planet Mercury. And had Titan formed anywhere else in the solar system, Titan would be a planet. But it just happened to form orbiting Saturn, and so is the largest moon of Saturn, actually the second largest moon in the solar system. Jupiter's moon Ganymede is a little bit larger. But Titan is unique in that it has a thick, dense atmosphere, mostly nitrogen, with some methane. And so it's the only moon with a thick, dense atmosphere in the solar system. Let's start and look at some of these little tiny shards. You can see they don't look like the spherical moons you're used to thinking about. In fact, Atlas is orbiting just outside Saturn's A-ring. Daphnis is here in the Keeler gap. Pan is orbiting in the Encke gap. And you'll notice they have skirts of material. They've basically accumulated skirts of ring particles. The rings are only 10 meters thick, so these skirts are around their equators. And you can see Atlas has a great big skirt. Here's maybe the parent shard, the parent moon from which it formed, and now it's just covered with ring particles up to the point where the balance between the moon's gravity and Saturn's gravity, they'd get pulled away, so they can only grow up to a certain size. So just very interesting to look at those. And in fact, we think these moons with all these ring particles are probably like rubble piles, accumulated bits of debris, perhaps from the early formation of the Saturn system, but maybe with a single sort of apparent core inside of it. Let me show you a little bit up close of Daphnis. Here's Daphnis in the Keeler gap, and it's launching this beautiful wave along the edge of the Keeler gap. And there's a similar wave, but it goes the opposite direction because of how the ring particles orbit. You can see it's actually starting to disconnect a little bit. And if blow up of Daphnis, you can see it's actually pulled a little tendril of ring particles away from the edge here, and you can see that maybe Daphnis has two different ridges. Maybe it's actually changed its orientation and accumulated ridges of particles, in two different orientations. Another very interesting moon is Titan. This is the view that Voyager had of Titan, this haze-enshrouded world that when you look in the visible wavelengths, you can't see through to the surface. And that was one of the reasons to send the Huygens probe. We didn't know, is Titan covered with a global ocean of liquid methane? Does it have craters like our moon? What does that surface look like? And so here's the Huygens probe. It first encountered Titan's atmosphere about 1,270 kilometers up, and then opened a little parachute. Lasted only for about 2.5 seconds. That drogue chute pulled out a larger parachute. We only stayed on that main large parachute for about 15 minutes because now Huygens is operating on batteries. So we had to get through to the surface in 2.5 hours before we were worried that the batteries might wear out. So we went to a smaller parachute for basically the bulk of the descent, the last 2 hours and 13 minutes, and then landed on the surface, and Huygens survived that landing and kept sending data back. As Cassini flew overhead, the Huygens probe was busy sending its pictures and its data all the way back. There were cameras, instruments to measure the pressure and temperature of the atmosphere. So 2.5 hours of descent, Cassini was able to receive another hour and 12 minutes of data. And then the way Titan was positioned, we could use the deep space stations here on the Earth, like the one in Tidbinbilla, to continue to pick up data from Huygens until the batteries grew too cold on the surface. So it remained alive on the surface for 3 hours and 14 minutes. Let me show you a little video of what that landing looked like the last 10 kilometers before the Huygens probe impacted. So here now we've gone through the haze. You can see what looks like evidence of little river channels. Here there's still some haze remaining as we got closer to the surface. The Huygens probe was spinning, and as it spun, the cameras were taking pictures to give us this landscape view until finally the Huygens probe under its parachute landed on the surface of Titan, and this is what we saw. Basically rounded icy pebbles. This one maybe perhaps the The Huygens probe kicked up and turned over a little bit, but the fact they were rounded told us that fluid flowed on the surface of Titan to make them rounded in a shape like this. And here's another view. You can see now the sizes. They were the ones closest were probably millimeter, centimeter size, and you could see out to the horizon. We had a lamp on board to give us the true color of the surface. We knew the spectral characteristics of that lamp, so we turned it on right before we landed. And so this is the color of Titan's atmosphere and of the surface. And here's a footprint on the moon, an astronaut, and a flag to give you an idea of the scale. You're looking all the way out to the horizon on Titan. And then you can see all of these river channels, these dendritic flow patterns. We think we landed in a dry stream bed on Titan. In fact, the bottom of the Huygens probe was warm. We actually saw that more gases, methane, ethane, came out of the surface as we were sitting there warming it up. Here's a view at the North Pole. There are a series of giant seas and also some smaller lakes. This sea is about 1.5 times larger than Lake Michigan, than one of the Great Lakes, about 100 meters deep, just filled with methane and ethane. Now imagine if we could build a pipeline long enough to go all the way to Titan. Our hydrocarbon worries would be over. We've just got lots of methane and ethane in these giant seas. And in other respects, Titan is Earth-like because there's also dunes. That methane gets broken apart by sunlight, kicks off a hydrogen that grows larger molecules. They grow large enough so that they fall down to the surface, these aerosols, and form long linear dunes. Also mountains, perhaps cryovolcanoes, water volcanoes that come out and supply the methane to the atmosphere. And this false color is showing you the flow pattern, perhaps, of this ancient cryovolcano. Clouds that form, methane plays the role on Titan that water plays on the Earth. You can have methane clouds that form, methane rains down to the surface, flows through river channels and into the lakes and seas. And then there's the dry riverbed that we got a first close-up view. And from this profile from Huygens, for all the rest of our flybys of Titan, that was our ground truth of what Titan looked like. We also saw clouds circling around. This is that you can see these are the giant seas at the North Pole. You can see these clouds circling around. We actually saw it rain on the surface of Titan and darken the surface, much like a sidewalk would be darkened in a rainstorm. And then we watched over a period of months as the methane evaporated again back into the atmosphere. This is something called a specular reflection. It's a point where the sunlight comes in and it exactly reflects off, telling us there was liquid on the surface in these seas. And then here's the little one of the methane clouds in false color. So here's what we think is going on for the cycle of what happens. There's maybe cryovolcanism puts methane up into the atmosphere. Some of it can form clouds and rain down and fill these lakes and seas. The sunlight kicks off hydrogen and that can grow into these larger and larger molecules, complex organics that then can go down and form the dunes. We saw a few impact craters, but they were in many cases very heavily eroded and weathered by the weather on Titan, like you'd have for the weather on the Earth. Now here's a very interesting view. You can see that the seas tend to be here on the right-hand side of Titan, and there's a bunch of tiny lakes. These are places we didn't have radar data, but a bunch of tiny lakes. And here's Ligeia Mare, that very large sea over here for comparison. Now if we stretch that out, here are these lakes, and it's so different because here river channels are flowing into these giant seas. But we looked very carefully, and there's really no evidence for river channels. So how do you fill up the tiny lakes at the North Pole? What creates them, and how do you fill them up? Well, one idea is maybe when Titan's weather was a little bit warmer, there was nitrogen in the surface, and that nitrogen sort of blew out and made these pits all over one side of Titan. And the pits, the material fell back and formed these ridges, and then when it rained, they could fill up with liquid methane. So very interesting, the dichotomy just at the North Pole there of Titan. Well, and one thing else interesting about this, we wonder, since it's liquid methane, could life perhaps form and thrive in liquid methane instead of liquid water? And so the astrobiologists on Earth got together and did some work and ran some equations. And so we wonder, could we have a very unique new form of life, perhaps in the methane seas. And Titan also has a global ocean of liquid water under its icy crust, and perhaps in that ocean you might be able to find life as well. And so for the moons, I just want to conclude talking about tiny Enceladus, a very special moon. You can see it's very small. Compared to the Earth and Moon, this is Enceladus. And here's a close-up view of it. There are 4 bluish tiger stripes at the South Pole. Now, when Voyager flew by in the 1980s, the South Pole was dark, and so we missed the fact that here are these tiger stripes, no craters. This surface must be very fresh and very young. And there's a lot of Enceladus here, which really doesn't show evidence of much in the way of craters at all, and just a few sparse craters as you go toward the north. Well, to give you a better idea of the size of Enceladus, here is Canberra and Sydney. And so that distance, there's the radius of Enceladus. That distance is a little bit greater than the radius of Enceladus. And here would be the radius of Enceladus across Australia. So this tiny world at 500 kilometers is very small. And so we thought for sure it'd be frozen solid, just like frozen like an ice cube. But why so bright and icy? And it's in the middle of the E-ring. So we looked in more detail at these tiger stripe fractures. They're about 130 kilometers long, about 2 kilometers wide. They have these big ridges of material that have come out and coated the sides of them. And it turns out in looking at some of the images, here's what we found. Geysers of water, vapor, and water ice spewing out, over 100 of them, from the South Pole of Enceladus. And here's a close-up view of some of those, over 100 different little vents coming out of these 4 tiger stripe fractures at the South Pole. And this is pointing to a liquid water reservoir. We know that Enceladus has a global ocean of liquid water underneath its icy crust, putting this material out into space. Now, of course, once we saw this, the first thing we said is we need to fly through that and sample it and taste it and figure out what it's made of and what does that tell us about the ocean on Enceladus. Here's another view. You can actually start to see the individual vents here coming out, spewing into space. And when we did fly through, 7 times we flew through, and we measured the composition of the particles and of the gas. The particles, it turns out, contained salts, sodium and potassium salts. The ocean is salty, with a pH very much like the saltiness of the Earth's oceans. We found complex hydrocarbons in this material as well. We also studied the gases, and not only did we see water, which is on the far left-hand side in the bright blue, but we also found ammonia and methane and some argon and very complex organic molecules. All of this coming out from these vents, coming from the ocean on Enceladus. And not only and most of the material falls back to the surface, and that's why there's so few craters. They've just been filled in. But the very tiniest particles, about 2 microns in size, here's Enceladus. They shoot out of the vents. You can see fingers of material that go on to form the E-ring. So we did find out what's the source of the E-ring. It's actually all of these jets coming out from the South Pole of Enceladus. So here's that view, an icy crust. Here's a global liquid water ocean that's salty and also contains hydrocarbons. We also found out that the ocean was there because we looked at 10 years of data, and Enceladus wobbles or librates more than it should if it's frozen solid. But if you take the rocky core and ocean and separate it from the icy crust, that allows it to wobble that much more. Also saw evidence of hydrothermal vents on the seafloor, and that was tremendously exciting. We could see an excess of methane, some molecular hydrogen that would come from a hydrothermal vent from studying them on Earth, and mostly these tiny nanosilica grains, that these grains form as the hot water comes out of the core, hits the cold ocean water on Enceladus, and precipitate into these tiny grains. So this material can only form at water near the boiling point. Another way to know about these hydrothermal vents. Now we have these hydrothermal vents here on the Earth. If you look at them, here's an area where the hot water is coming out and condensing minerals, very much like what we saw with Cassini coming out of Enceladus's vents. There's also something called black smoker, so it looks like smoke as the water comes boiling out and interacts with the cold seawater. Now, this is deep in the ocean. There's no sunlight. It's very dark. It's near some of these deep trenches and places in the Earth's crust. If you look closely, though, there's enough energy, heat energy and nutrients coming out of these vents to have all sorts of life that is possible. Little crabs, tube worms, blind fish. And so that makes us wonder, could you find life, perhaps, in the ocean on Enceladus? Now, Cassini didn't carry any instruments to look for life. We had no idea we'd have to do that. But to go back with the instruments to look for those long amino acids and the evidence that there might be life on this moon. Well, finally, Cassini was running out of fuel, and it was time to find a way to end the mission. And so that's when we came up with the idea for the grand finale and a good way to say goodbye to Cassini. And we did this because in many ways, Cassini was a victim of its own success by discovering 2 potential worlds for life, Enceladus and Titan, with conditions where you might possibly have life. NASA Planetary Protection said, you can't run into these moons, you can't risk it when you're out of fuel. So you have to find some way either to leave the Saturn system with Cassini or to send Cassini into Saturn. And so when the scientists heard they had a chance to actually dive in between the rings and the planet for 22 orbits, they said, that's where we want to go. That's the mission. That's the way we want to end Cassini's adventure at Saturn. And so that's what we did. With one Titan flyby, we were able to hop all the way across the rings, and then for 22 orbits, orbit in that gap. We started near the outside of the gap, and the orbit slowly walked in closer to Saturn until a distant Titan flyby, we called it the Titan Goodbye Kiss, sent us on that final orbit into Saturn's atmosphere. But along the way, in those 22 orbits, we made some amazing discoveries. I won't go through all of them, but just highlight a few. We found a new radiation belt. We found ring particles falling into Saturn. We found that the magnetic axis and the spin axis of the planet were almost perfectly aligned. A big surprise. We didn't know it would come out to be that close. Currents connected the rings to the atmosphere of Saturn, and some of the charged dust actually spirals in as ring rain. And perhaps most astonishing, by going into that gap, we could measure the mass of the rings by themselves and get an idea for how old that the rings might be. The less massive, the less likely they could survive being eroded away by micrometeorite bombardment. And so we discovered the rings might be only 10 to 100 million years old. And you think about, well, what was happening on Earth 10 or up to 100 million years ago? Well, that was the time of the dinosaurs. So maybe if the dinosaurs had telescopes, they looked at Saturn one day and said, hey, where did those come from? Where did the rings of Saturn come from? So let me talk a little bit about Cassini's final 90 seconds. As I said here, at Tidbinbilla at the Canberra complex is where those final seconds of data came back from Cassini. And we were all gathered in a room together to watch that final signal. Here's what it looked like. That green peak is telling us we're communicating with Cassini. And as that peak goes away, first an X band and then an S band, we knew that Cassini could no longer hold its antenna pointed at the Earth, and that the atmosphere had grown too thick and had pulled it away, and very quickly then the spacecraft had disappeared. So we sat there, we were cheering, come on, last a little bit longer, Cassini, you can do it. And then here's sort of what erupted. It was a very emotional time at JPL. People hugging each other. We had purple handkerchiefs that we could use that matched our purple shirts to dab our eyes, and it was a very emotional time at JPL to say goodbye. In fact, we had taken a picture a little bit earlier. This is the Cassini team, everyone at JPL, everyone now saying goodbye, waving goodbye to Cassini. And I actually had my 2 daughters, now grown up, Jennifer and Jessica, and little granddaughter Audrey at her first big spacecraft event for the end of the Cassini mission. And one of the things that we brought with us in 2016 was this poster to thank everyone at the DSN station here in Canberra for all of the work they had done in supporting Cassini over the 13 years of the mission, but also the 7 years of cruise to go all the way out to Saturn. So just incredible support from that very remarkable team. And I'd like to share with you a movie that highlights many of the things I've shared with you, and maybe a few new things as well about what you'll see leading up to Cassini's grand finale.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft was running out of fuel. And so, to protect the moons of Saturn that could have conditions suitable for life, a spectacular end was planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. We have cleared the tower. Pitch program is in. Roll program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
SOI burn attitude or pointing position. Light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds, where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. But before its work was done, Cassini had one last daring assignment. Cassini's grand finale was a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braved this unexplored region, Cassini found new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini plunged into Saturn, fighting to keep its antenna pointed at Earth as it transmitted its farewell. Until, in the skies of Saturn, its journey ended, with Cassini becoming part of the planet itself.
I feel very privileged to have been part of such an incredible mission of exploration and discovery. And so many good things happened. We did such a good job with our coverage and the data coming down that a year later, a group of us actually went up and received the Emmy Award for Cassini for our coverage of the grand finale. And so that was really a lot of fun. I had a chance to be there that evening, and the big thing was, I want to hold the Emmy. Give me a chance to hold it. So that was very, very exciting. And we learned so much about Saturn and its moon Titan, and so many questions remain unanswered. And it turns out that I think it would be great to go back, and NASA agrees with me. They recently selected through the New Frontiers process another mission to go back to Titan. And that mission is called Dragonfly. Dragonfly is a quadcopter to fly in this very dense atmosphere. It's a pressure of 1.5 times the pressure on the Earth. The gravity is a lot less. So it'd be very easy to fly around in different places on Titan, carrying a package to look at the chemistry going on, look for possibilities, that you might have evidence for life. And so that mission is headed to Saturn, probably arriving in the 2030s sometime. It takes a long time to get all the way out to Saturn. And then looking ahead to the future, maybe the distant, maybe the not so distant future, maybe someday, we'll actually send the equivalent of cruise liners out to explore the solar system for a grand tour of our solar system. And with that, I'd be very happy to take questions. Thank you very much.